Hi, this is Dane Quinn from the University of Akron, and today I would like to talk to you a little bit about what you can do with a position analysis once you're finished. Here we have a mechanism that's essentially a 4-bar linkage, but link 3 is pinned not at the end, but somewhere in the intermediate point at A. So we have an input link L2 that is connected to the ground, and then link 3, the distance between A and B, I'll assume to be L3. However, the total length of this bar is L3 plus D, and this distance D kind of extends out to the left. And then link 3 is connected to link 4 at B. So if I'm interested in the position of P, then I could write the position of P with respect to, say, O2 as, well, there's going to be this vector. The natural way of expressing this, though, is a vector from O2 to A, and then from A to P. So again, that vector position of P with respect to O2, I can write as the position of A with respect to O2. So that's kind of along link 2. And then the position of P with respect to A. So now if I go through and I look at this linkage again, this is not the loop closure equation. Instead, the loop closure equation is kind of this 4-bar linkage that's embedded within. So here we might identify the loop closure equation as the vector from, again, O2 to A, and then A to B equals the position of O3 with respect to O2, and then B with respect to O3. So the loop closure equation is as follows. The position of A with respect to O2 plus the position of B with respect to A is equal to the position of O4 with respect to O2 plus the position of B with respect to O4. Right, so that's given here on the right. So now let's go through and identify some of these vectors and directions, and let's actually put some structure to this loop closure equation. So here we'll identify I2 as the direction of link 2, and then J2 there. We can define I3 as the direction from A to B, and that's accompanied by J3. And then finally, I4 and J4 are as given. And then, of course, we have I and J fixed in the ground. So along with this, right, we'll have an angle theta 2, an angle theta 4, and an angle theta 3. Here, let's assume that theta 2 is known, and what we want is the position of P with respect to O2. Well, in terms of these directions, we can write this as L2 in the I2 direction, because again, that's A with respect to O2, and then minus D in the I3 direction, because P is in the minus I3 direction by a distance of D relative to A. So now also, again, writing the loop closure equation in terms of these directions, we have L2 I2 plus L3 I3 equals L1 I plus L is determine I3 from the loop closure equation. So that we can then use it to find the position of P with respect to O2. So again, this is what I mean by following a position analysis. So we carry through the loop closure equation, we go through, and eventually we'll solve for theta 3. And then once we know theta 3, we can go back and use that to find the position of P with respect to O2. Right, so let's do that. Here, we're just interested in theta 3, so it makes sense to eliminate theta 4, giving us one equation in terms of theta 3 that can then be solved for theta 3 directly. Right, so to do that, we'll isolate L4. This is our kind of standard trick here. L4 is equal to L2 in the I2 direction, plus L3 in the I3 direction, minus L1 in the I direction. And then we'll take the magnitude squared of both sides. So on the left-hand side, we end up with L4 squared, right, because this vector has length L4 and the direction is unknown. On the right-hand side, and I'm just going to write this out, right? I've worked it out. Maybe now would be a good time for you to pause the video solution and work out the magnitude of the right-hand side, right? But you should find something that looks like L2 squared plus 2 L2 L3. And then there's a term that comes from I2 dot I3 here, which becomes cosine of theta 2, cosine of theta 3, plus sine of theta 2, sine of theta 3. We have plus L3 squared. We have a term that comes from L1 dot L3, so that is minus 2 L1 L3 cosine of theta 3 plus L1 squared. And then finally we have minus 2 L1 L2 cosine of theta 2. So I will point out that the only unknown here is theta 3. We've eliminated theta 4 by writing the loop closure equation in this way and then taking the magnitude. Okay, so now we still have to solve this. On this slide, I've rewritten the equation that depends only on theta 3. Notice that I've combined all the terms that are actually independent of theta 3 here. And then I've collected the coefficient of cosine theta 3 in this combination. And then this represents the cosine of sine coefficients. So notice that everything in these yellow boxes are known because theta 2 is the input link angle. That's known. All these distances are known. And then we want to solve for theta 3. We know how to do this. I've had video lectures on exactly this sort of equation. So I'm not going to go through the procedure of solving this again here. I would instead refer you back to the earlier lecture on the 4-bar linkage. But it's enough to say that for any input angle theta 2, we can solve for theta 3. Right? We know how to solve equations like this. I've given you a couple different approaches. So that's the idea. Given theta 2 and all these lengths, solve for theta 3, and then we have the configuration of the mechanism. Notice that we'd also have to go back and solve for theta 4 as well. But here in gray, I've shown one configuration, and this is with theta 2 60 degrees. This is the gray configuration that we saw earlier. But then if I change theta 2 to, say, 180 degrees, I get a new configuration. That's given here in purple. Increasing theta 2 further to, say, 300 degrees gives us this yellow configuration. For any angle theta 2, I can do this. I can solve for theta 3 and ultimately the configuration of the mechanism. What I'm really interested in this problem, though, is the position of P. Right? So P is over here at the end of the bar. And I'll remind you of some of the dimensions. This bar that we called length 3 is pinned somewhere in the middle. Its total length is actually D plus L3. L3 was the distance between A and B. sort of to be familiar with the analysis that we had started off with 4-bar linkages. But then we have this extra bit that extends down to the left. And that's a distance d away from A. Remember, A was here, O2 is there. So we're really interested, again, in the position of P with respect to O2. Right? So that's this vector here. We're going to express that, though, in terms of known directions and known vectors. Right? So as we solve for this mechanism, we can find the position of A with respect to O2, and then using theta 3 that we solved for above, we can find the position of P with respect to A. Right? So this is the position of P with respect to A. This is the position of A with respect to O2. And ultimately, we're interested in the position of P with respect to O2. So again, if I know the configuration, theta 2 and theta 3, then this vector that I'm interested in is L2, right, in the I2 direction, that's this, minus D in the I3 direction. Because remember, I3 was directed to the right, and of course I2 was along link 2. So, how do we express this final outcome? Well, we make use of our direction transformations. So I2 is cosine of theta 2 in the I direction, plus sine of theta 2 in the j direction. I3 is cosine of theta 3 in the I direction, plus sine of theta 3 in the j direction. And again, this is how we defined I2 and I3. So as a result, R of P with respect to O2, so the position of P with respect to O2, is L2 in the I2 direction, so that's cosine plus sine, minus D in the I3 direction, which is cosine of theta 3i, plus sine of theta 3j. And so we can just combine the I and j coefficients, and we get L2 cosine theta 2 minus D cosine of theta 3 in the I direction, plus L2 sine of theta 2 minus D sine of theta 3 in the j direction. And that's what I've shown here in this dashed line. This is the path of point P as theta 2 varies, right? So as theta 2 moves around, essentially P follows this dashed line, and it's given over here to the right. Now, you couldn't start off the problem and figure out what this path was. You have to go through the position analysis first so that you know the configuration, in particular so that you know theta 3. Theta 2 is given, right? But theta 3 comes from solutions of the loop closure equation and this equation up at the top. So whenever we're asked for a position, we have to go through the position analysis. We have to write out the loop closure equation. We have to solve for the unknown variables. And then we go back and we use that to answer the question that we've been asked. In this case, it was find the path of P, say. So again, the loop closure equation, all this kinematic analysis that we've done, right? That's a step, and an important step, along the way to answering the questions that we've been asked about the configuration of the linkage. So let's see where else we can use position, right? And namely, that's displacement, right? So what is displacement? It's the change in the position of a point between two different configurations. So here I've given essentially an inversion of a slider crank, and I'd like to know ultimately the displacement of the end of this bar as well between two different configurations. So the position of P with, say, O2 is equal to L2 I2 plus L3 I3, where we're going to define I2 as a long link 2. Right, so I2 and J2 will be like this. And we also have theta 2, like so. Of course, we have I and J fixed in the ground. And then we'll have I3 along link 3 and J3 perpendicular to that. Here, this angle, theta 3, essentially orients I3 and J3 with respect to I and J. And then finally, notice that the distance between A and O3 can change. Right, so I need to know that length, and we'll call it Z. So as a result, this is the position of P with respect to O2, so that would be a vector from, say, here to here. Let's go and write that out. Right, so if we're asked for the displacement of P, essentially it's the change in this vector. But just like before, we need to go through and determine the loop closure equation. And that is different, right? That's going to be this vector, or this vector equation. It's A with respect to O2 plus O3 with respect to A equals O3 with respect to O2. So here, the loop closure equation, we could say R of A with respect to O2 plus R of O3 with respect to A is equal to R of O3 with respect to O2, right? Or in terms of these directions and coordinates and such, L2 I2 plus Z I3 equals L1 in the I direction. I will note, and this will be, I'll note this again later, I3 and J3, that's defined if theta 3 positive rotates clockwise, while I2 and J2 rotate with theta 2 positive in the counterclockwise direction. So here, again, if I'm interested in solving for the position, we need to solve for theta 3. And given theta 3, I can determine I3. Theta 2 is the input, right? So then I can find the position. So in terms of our loop closure equation, right, our procedure then would be to eliminate the other unknown, which in this case is Z. So how do we eliminate an unknown length? Well, we dot with a direction, J3. And you might say, well, look, if I do that, I get rid of the theta 3 part as well. And yes, I3 dot J3 is equal to 0. However, you also end up putting theta 3 back into the equation as you dot J3 with I2 and I and J3. So you still end up with theta 3 in the equation. And the result looks like this. L2, I2 dot J3. That's cosine of theta 2, sine of theta 3, plus sine of theta 3, sine of theta 2, cosine of theta 3. Here, I will remind you that I2 is cosine plus sine, and J3 is sine of theta 3, I plus cosine of theta 3, J. right? So when I dot these two together, I get this term. This also happens to be equal to the sine of theta 2 plus theta 3. And that's going to be equal to L1 I dot J3, right there, or right there, sine of theta 3. So we can solve this. We can solve this for theta 3. And what we find is that tangent of theta 3 is equal to L2 sine of theta 2 divided by L1 minus L2 cosine of theta 2. Right, so I just solved this equation for tangent of theta 3. And as a result, what we find is that r of p with respect to O2 is, of course, L2 I2 plus L3 I3. And over here, I will tell you what I3 is again. It's cosine theta 3i minus sine of theta 3j. And this reduces then to, so I'll take this for I2 and this for I3 and plug them in. Collect terms of I and j. L2 cosine theta 2 plus L3 cosine of theta 3 in the I direction plus L2 sine of theta 2 minus L3 sine of theta 3 in the j direction. So again, in this case, L3 is the total length of this bar. And the loop closure equation just depends on this distance z in the I3, which is the distance between A and O3. And finally, we have the position of P with respect to O2. And in order to solve that, we would need the results from our position analysis and the loop closure equation so that we can solve for theta 3. So here it is again, position of P with respect to O2 and our solution to solve for theta 3. We're interested in the displacement. Displacement is the change in position, right? So let's say we have an angle theta 2, right? So again, this is going to be theta 2. So this is theta 2 at time t1 to theta 2 at time t2, right? So maybe in this case, theta 2 starts off down here. Notice that this angle is less than 0, right? Because theta 2 was defined positive clockwise. And then it goes to a larger angle, right? So this will be theta 2 at time t2, which in this case is greater than 0. Then the displacement's always represented as delta rp. This large delta indicates, well, it's just a standard notation for change. So it's the position of P with respect to O2 at time t2, right, final, minus initial. Right, so again, it's the final position, right? So in particular, this would be the final position. This would be P at time t2. This would be P at time t1. So the displacement would be this position minus that position, or this vector. So really, what do? We use the value of theta 2 at the final time, calculate theta 3, right? Find the position. Do the same at the initial time, find the position, and subtract one from another. So here I've given some numerical values. L1, that's the distance between O2 and O3, is 60 centimeters. L2 is going to be 30 centimeters. And L3, which is this total distance of the link, is 90 centimeters. And I want to find the displacement from minus 45. Remember, as shown, this is a negative input angle to 105 degrees, like I said. So these are the configurations shown. So again, I've worked through all this. Theta 2 equals minus 45. Go through, calculate tangent of theta 3, and we get minus 0.547, which actually gives us theta 3 as, so this is theta 3 at T1, minus 28.68 degrees. So that's going to be this initial angle, right? So this is theta 3 at time T1. Notice that because we define theta 3 positive clockwise, this is actually a negative angle. And sure enough, theta 3 is minus 28.68 degrees. At the final time, theta 2 is 105 degrees, like sort of shown over here. Our tangent is 0.428, and as a result, theta 3 at the final time can be solved as 23.15 degrees. That represents this angle. So we have theta 3 at T2. And again, even though this is down, it's a positive theta 3 because that's the way we define theta 3. All right, I'll go back and kind of remind you. Theta 3 is defined positive. Well, if theta 3 is positive, then I3 is defined sort of down and to the right. So again, take all this stuff, throw it in here to the position, and then these are our two position vectors. At T1, right, so that's up here, we get 100.17 centimeters and almost 22 centimeters up. At the final position, we get basically almost 75 centimeters across, and then minus 6.40 centimeters in the J direction. So putting all this stuff together, right, we see that the displacement of P is minus 25.18 centimeters in the I direction, right? So that's going to be this component to the left, and then minus 28.38 centimeters in the J direction. So we're able to find our displacement, or the change in position of P, from these two input configurations, T1 to T2. So here we have basically sort of two examples of how we can use position after we solve for our position analysis, our kinematic analysis. We can take those variables and use them to calculate other positions, displacements, that kind of thing. Right. So that's it. Thanks a lot, and I will talk to you again. Bye. Baby 300 degrees gives us this yellow configuration, and I could do this for any angle. Dogs agree. Hey, I'm in the middle of something. Can you go sit down? Go back to sleep. Okay, I'll pet you both. Okay, go lie down. No, go. Oakley.